Let's look at the tubular reabsorption. Now remember, almost all the energy expended by the nephrons, which are just epithelial cells making tubes in the kidneys, almost all that energy is expended at reabsorption. Not a whole lot is pumped into the tube and out of the body. So let's see how this reabsorption occurs. You got to go back to your process as described on the cell previously. Number one is simple diffusion, just materials moving from high to low concentration. They're lipid soluble, they're going to move through the cells quite easily, if not, not so much. There's also facilitated diffusion. Now the facilitator will be a protein helper in the cell membrane. So the cell can build proteins that will let things diffuse, which ordinarily would not. Number three is active transport. Remember, this is the expenditure of energy to move material against diffusion. This is how the cell can set up concentration gradients of different materials. After active transport, sym and antiport can also occur. So you got to have the active first. But if you look at symport, which is the same as co-transport, that's where two materials are being moved through a protein in the same direction at the same time. The antiport or countertransport is where two materials are going through one of the proteins, but in different directions. We'll see examples of all these. And then, of course, lastly, there's osmosis, the movement of water from high to low concentration. And remember, wherever the solutes are moved to, the water's going to follow. So again, you look at the different parts of the nephron. Bowman's capsule, there's no reabsorption there. That's where the filtration happened inside of it, crossed the walls of those glomeruli. Then the rest of the nephron is primarily about reabsorption. Proximal tubule, loop of Henle, distal tubule, and then the collecting ducts. You're going to reabsorb over 99% of this material. So think about these epithelial cells lining these tubes as having three different surfaces. One side of the cell faces the inside of the tube. Well, that's where the filtrate is at, so we'll call that filtrate side. Another side is opposite of the tube, so that's going to be back on the body or interstitial side. And then, of course, you got lateral surfaces in between. Now, these epithelial cells, like others, have lots of proteins binding them together, so not a lot's going to get in between them. So the cells will get to decide what's going to pass through them. What you see typed up right here is how you have reabsorption in the proximal part of the tube. And remember, in the proximal part of the nephron, that's where you're going to get 65% of that filtrate pulled back into the body. So if you look at this material here, let's see what happens on this little picture. If you want all this reabsorption to occur, you got to start with the sodium-potassium exchange pump up here on the interstitial side. Now remember your goal. Say this is the inside of the nephron. This is the filtrate side. This is the body, the interstitial side. You got to get almost all this material back into the body. Again, what you put in here is plasma. Now you call it filtrate. Over 99% of it's useful material, so you don't want to lose it. So if you want to get this stuff back into the body, you got to start with the sodium-potassium exchange pump. Very common example of active transport in the body. Now remember, this is the interstitial side up here. This is the inside of the nephron right here. So you always see this sodium-potassium pump here on the interstitial side. And remember, every time it burns up ATP, it'll pump 3 sodium out and 2 potassium in. Now what's important is that the sodium's being pumped out of the cell. That's going to create a sodium concentration gradient. In other words, there's going to be more of it on the outside of the cell and less of it on the inside because the cell's pumping it out. Now that sodium wants to come back in, but there's no way for sodium to get back into the cell on the interstitial side. But there is a way for sodium to get back in from the inside of the nephron. And that's where we have these little co-transporters shown in yellow. So sodium will move back down its concentration gradient, coming from the inside of the nephron where there's more sodium to the inside of the cell where there's less. Again, this active transporter in red set up this gradient. So what the cell did was pump the sodium out of the tube on the interstitial side, knowing that sodium would come back in from the filtrate side. So as that sodium comes back in these co-transporters, moving down its concentration gradient, that provides the power to move useful materials into the cell. Again, you want to hold on to most of these ions, glucose, amino acids, and other useful materials. So the cells pump sodium out on one side, knowing it would come in on the opposite and pull the good useful materials with it right there. There's your code transporters getting this useful material into the cell. So now you move the useful material into the cell. Now you got to get it back to the interstitial side. Well, that's where these facilitated diffusers come in. You're going to build up a high concentration of this useful material in the cell. It won't diffuse on its own, but the cell can build proteins that will let it diffuse. So as you move this material in through the co-transporters, they build up to high levels. There's less of it over here on the interstitial side, and the facilitated diffusers let that material diffuse from high to low. So look what you've done. Move your useful materials back to the interstitial side, where the peritubular capillaries, the second set of capillaries, will pick that stuff right back up. And all you need now are aquaporins. Those are water channels. And as you move these solutes from the inside of the nephron back into the body, the water will follow it. And that'll let you reabsorb a large amount of material. Again, in the proximal part, there's more surface area than what you have in the other parts of the nephron. So that's going to allow you on average to get 65% of this material reabsorbed back into the body. And again, that is the goal of the kidneys, to hold on to that good useful stuff. Now look at these carrier molecules like we see in this previous picture. Remember, there's only so many of these proteins, so only so much material can be transported. If you look at just one thing, glucose, those glucose transporters can be oversaturated. In other words, if we consume large amounts of sugar, or we just for whatever reason like diabetes mellitus have too much of it in the body, too much will be put into the nephron, and there's more glucose here than what we have transporters for. That is the only time that glucose escapes, never on purpose. The kidneys do not get rid of glucose intentionally, only when there's too much sugar to be moved and the cell can't pump it back quick enough. Then some of it escapes unintentionally. Again, that's a big misconception with things like diabetes mellitus. And as all this sugar escapes out of the body, water follows it, because water follows solutes. That is why diabetics have such a high urine output. They're losing a solute they shouldn't, and the water's following it. Of course, they have to drink a lot of fluids to replace that material. So there's the pictures we had before with the links to the guide too.